All right, guys, hello and welcome to another physics video lecture. Today we are going to be talking about universal gravitation. All right, so let me move that real fast. All right, so let's give a real quick history of how humans viewed gravity. One of the first theories of gravity was from a guy named Aristotle. Again, you don't have to write this down. This is just for fun. Aristotle believed that elements wanted to go back to where they came from, right? So he thought that solid things were made of earth, so when you drop them, they went to the earth. And he thought that when you burnt things, fire wanted to return to the sky to go back to the sun. Not a bad guess for 2,500 years ago, all right? Next up, we got Galileo. Galileo is the guy who realized that when things fall, right, they fall, okay, with the same acceleration. Good job, Galileo, okay? Robert Hooke is the guy that noticed that as masses get farther apart, the force of gravity is less between them. And our main man, Sir Isaac Newton, is the one that put it all together in this equation that we're about to look at today. The big theory is that an apple hit him on the head and this came to him. I don't know whether or not that's true, but we're going to look at his theory nonetheless. All right, so this is Newton's theory of universal gravitation. Looks complicated, but all we got to do is figure out how to put numbers in it, how to get those numbers into the calculator, and how to find our answer. Okay? The first thing we see here is this big G. The big G is called the gravitational constant, all right? This number never changes, and you always have it on your equation sheet on that third page. It is 6.67 times 10 to the negative 11th. Don't worry about that, okay? That's the unit that cancels the rest of the units out, and we don't need to know it. So you just need to know 6.67 times 10 to the negative 11th, Newton's meter squared divided by kilogram squared. All right. M1 is the mass of the first object, M2 is the mass of the second object, and D is the distance between those two objects' centers. That is very important, okay? When you measure gravity, you always measure from the center of the object. I'm sure you've heard the term center of gravity before, and that's very true, okay? This is why when you're playing football and you don't want to get tackled, you squat down. The lower your center of gravity is to the ground, the harder it is to knock you over, all right? Same reason why it's easier for a big pickup truck to flip over than a little sports car, okay? The big thing about distance here is that we square the distance, so you gotta remember to do that, all right? So when we're filling these out, you gotta remember to always multiply by 6.67 times 10 to the negative 11th. You gotta include both masses, and you gotta square the distance. All right, so I do want you to write this down. So pause the video, copy this. All right, very important. Next up, I would like for you to draw this diagram, okay? Because this shows you a lot. This shows you the two masses. It shows you the distance between the masses. Specifically, it's the distance between the masses' centers. Okay, you always measure from the center of gravity. And then it shows you the equation. Isn't that lovely? Copy this down. Here's a video you can watch that helps explain some of this. We're going to blow past it because I want this to be as short as possible. All right, two big takeaways that we're going to see mathematically in a second. Number one, the force is directly proportional to the masses, meaning they are direct. So as the mass of an object gets bigger, its force of gravity gets bigger, right? That makes sense. The Earth is bigger than the moon, so the moon revolves around the Earth. The sun is bigger than the Earth, so the Earth revolves around the sun, right? The bigger you are, the more gravity you have, all right? And as we're about to see here, this means that if you double the mass, you double the force, right? Twice as much mass equals twice as much force. The distance, because it is a square, is even more powerful, all right? The force is inversely proportional to the square of the distance, okay? The distance squared. Remember, we square the distance? And what that means is that as the distance between two objects gets bigger, the force of gravity gets smaller. The farther you are from something, the less gravity it has, right? And because it's a square, that means that if you double the distance, okay, you divide the, oh, did I say the mass is divided by 4? Oh, that should say the force is divided by 4. Hold on one second. Fix in real time. Look at that, back on track. Okay, so when the distance doubles, the force of gravity is divided by 4. Okay, so when you double the distance, that gravity is divided by 4 because it's a square. So again, here's just another way to look at this. Okay, mass and distance are all we care about. All right, as the masses get bigger, the force of gravity increases, and as the distance between them gets bigger, the force of gravity decreases. Here, the force of gravity is represented with these little red arrows. Right? Look at this. This is a small object. As the object gets bigger, the arrow gets bigger. As the objects get farther away from each other, the arrows get smaller. Okay? As the objects get bigger, the force of gravity gets bigger. As the objects get farther away from each other, the force of gravity gets smaller. So, real quick, let's see if you can pick this out. I know this is kind of fuzzy. Here we have 3 sets of objects, A, B, and C. Real quick, can you tell me which one of these has the greatest force of gravity? Take a look. Did you say A? Because if you did, good job. How do we know it's A? Well, look, the distance between all of the objects is the same. The distance is 1, okay? So if the distance is the same, all we care about is the mass. And looky here, A has the 2 biggest masses. The biggest mass means A has the greatest force of gravity. Which one has the smallest force of gravity? That would be C, because C has the smallest masses. Right? Pretty easy. So this question says, what happens to the gravitational force, or the force of gravity, between the moon and the Earth if the distance was doubled? So if we double the distance, what happens to that force of gravity? We already answered this, but I'm going to show you how to figure it out mathematically. Okay? So the force of gravity is equal to I'm going to write it like this, just because it's easier to see. The gravitational constant times mass 1 times mass 2 divided by the distance squared. Now, here's the thing about constants. When you're doing these kinds of problems and seeing what happens if you double something or triple something, you don't care about constants. They always stay the same. Okay? So we don't care about big G right now. And what we're going to do is the same thing we did last time. We're going to set everything equal to 0. So we're going to say that mass 1 is 1. Or sorry, did I say 0? We're going to set everything equal to 1. Mass 1 is 1. Mass 2 is 1. And we're going to say the distance is 1 squared. You can bust out your calculator if you want to see this, but 1 times 1 is 1. 1 times 1 squared is 1. And 1 divided by 1 is 1. So our force, when everything is set to equal, is equal to 1. All right? Now we're going to do what this tells us to do, and we are going to double the distance. So instead of our distance being 1 squared, now our distance, so this is example 1, now 2, okay? Now we still have mass 1 is 1, mass 2 is 1, but now the distance is doubled. So instead of 1, the distance is now 2 squared. 1 times 1 is still 1, and 2 squared, or 2 times 2, is 4. So look, here was our original force, 1 Newton. Now we have 1/4 of a Newton. So by doubling the distance, we divided the force by 4. So let's look at another one of these problems, because I do all of these the same. I think this is the best way. All right, what happens to the gravitational force if the mass of the Earth and Moon was doubled? If we doubled both of their masses? Okay, so again, force of gravity equals big G times M1 times M2 divided by the distance squared. So our original bet here, I'll put it here. Remember, we don't care about constants because they always stay the same. They never change. So let's say the mass of the Earth is 1 times the mass of the Moon is 1 divided by the distance between them is 1 squared. Again, that equals 1. What happens if we double the mass of the Earth and the Moon? Okay. Well, if we double both of them, this is where it gets interesting. Okay. That means now instead of the mass of the Earth being 1, now the mass of the Earth is 2. Instead of the mass of the Moon being 1, now the mass of the Moon is 2. And our distance remains the same. It's 1 squared. 2 times 2 is 4, and 1 squared is 1. So now our mass, or our force of gravity, went from being 1 to being 4. And that's because we doubled both of the masses. Does that make sense? If we just doubled one of the masses, we would double just that force. Okay, we would only double the force. But we doubled both of the masses, so we multiplied it by 4. You see questions like this on the ACP. You'll see these on your bell ringer, or sorry, on your DOLs and bell ringers. Okay, and you just got to remember that if you just plug the numbers in, you will find the right answer. Okay, and you may see ones like I said earlier, where if you double the mass, okay, you end up doubling the distance. But that's quite not true. It's interesting, right? All right, guys, so let's look at scientific notation. We're going to work with really big and really small numbers. So, some of these numbers are really, really big. Those are what have positive exponents. So an example of a positive exponent is 1 times 10 to the 20th, okay? You would write that like this. And the reason we use scientific notation is because I am not writing this number down. Okay, this is a 1 followed by 20 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yes. Okay? So that's a really big number. That is a positive exponent. And all this is this is the number 1 times 10 20 times. So every time you multiply by 10, you get another 0. 1 times 10 is 10. 10 times 10 is 100, 100 times 10 is 1,000. And you do that 20 times and you get this number, which is like 100 quintillion. I'm not making that up. Negative exponents give you really, really small numbers. So instead of 1 times 10 to the 20th, if you have 1 times 10 to the negative 20th, what we now have is we have 19 zeros and then 1. Why 19 zeros? Because the way this works is you move the decimal. So watch. I'm going to move the decimal 20 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20. And the decimal, boop, is right there where it's supposed to be, behind the 1. So the thing to remember is that negative exponents give you really, really small numbers, and positive exponents give you really big numbers. This is so much easier to remember than all this like right and left stuff. Okay? Just remember that if you move the decimal because the number is really big, you're going to get a positive exponent, and if you move the decimal because the number is really small, you are going to get a negative exponent. How do we do it? Well, number 1 is this first number. You can only have one number in front of the decimal, so it'll be like 1.0 times 10 to the negative 20th, or 3.2 times 10 to the negative 15th, or whatever. But this first number only has one number in front of the decimal, and then you do what I just did. You count the number of spaces you move the decimal. Right? So like here, we have 4 times 10 to the 10th, so the decimal was here, and we move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. So now we have 4.0 times 10 to the 10th. Why is this positive 10? Because this is a huge number. Big numbers have positive exponents, right? If it was a really small number, that would be negative. All right, so now let's do some problems to show you how to use this equation. This Looks complicated, I understand, but what you gotta remember is that all we're doing here is putting these numbers into a calculator, okay? We're not moving anything around, we're not playing with the equation, we're just learning how to put the complicated numbers into the calculator. All right, so step number one is write down everything you know. What is the gravitational force between the Earth and the Moon? Okay, I did some of the work for you. The mass of the Earth is equal to 6.0 times 10 to the 24th kilograms. That's a lot of kilograms. This is one of the constants on your reference sheet, so you always have this. The mass of the Moon is 7.4 times 10 to the 22nd kilograms, quite a bit smaller, okay? The distance between their centers, remember, look here, you measure from the center of the objects, is 3.8 times 10 to the 8th meters. And again, we always have big G, which is 6.67 times 10 to the negative 11 newtons times meter squared divided by kilogram squared. Okay? So, we set this up. Here is our equation. So I'm just going to put my numbers in. All right? So my force of gravity is going to be equal to big G. And notice I put these all in parentheses. 6.67 times 10 to the negative 11th. We're going to multiply that by the mass of Earth, which is 6.0 times 10 to the 24th, times the mass of the Moon. Can I fit it? 7.4 times 10 to the 22nd. I should have made that one smaller. All right, this all goes on the top of the fraction. Big G, mass number 1, mass number 2. All right? Then we're going to divide all of that by the distance between their centers, which is 3.8 times 10 to the 8th. And the mistake everybody always makes is to not square this. Remember, you got to square the distance. So one of the biggest tricks with using these big numbers is you got to put parentheses around all of them. All right? The second big trick is that when you're entering them into your calculator, you gotta make sure that you do all of the top multiplication first and then the bottom multiplication, all right? Now, if I set this up right, I should be able to, okay, let me see if I can bring my calculator over here. All right, yes. This smaller? Okay, so hopefully you guys can see this. All right, so here we go. So what I'm going to do here is I'm actually going to type this in. So watch this. I can type a lot of this in. So watch this. First thing I'm going to do is I'm going to type a parenthesis. Look at that. You can click the parenthesis. It's right here. I know you can't see that underneath there, but that's a parenthesis. And I'm going to type this in. So look, 6.67 times, here we go, 10 to the negative 11th. How do we do that? You go to A to the B. When you click this, you see how it jumps up there? Then you have to type negative 11. If you click it again, oh, you don't want to do that. What you want to do here is actually, you want to just push the forward arrow, and it goes from the exponent down so you can close that parentheses, which is right underneath the cosine. Boom, there's your first number. Now we're going to hit times. Parentheses, 6.0 times 10, a to the b, 24. Then you're going to hit the down or the forward arrow. Notice it jumps down out of that exponent, and we're going to close that parenthesis. And then we got one more, times, parenthesis, 7.4 times 10, a to the b, 22. Press the down arrow, and then hit close parentheses. And now you hit this big enter button. Okay, so this is your answer. That's a huge number. That's 3 with 37 zeros after it. I have no idea how you even say that. Watch what happens. When I hit enter, okay, there is your answer. Now, we want to divide that huge number by this. Here is a great trick. Instead of retyping this number, you can just hit answer and watch what happens. It gives me the answer from that last calculation. And now I can take this big number and hit divided by, and look what it does. right? It divides it. So now what I'm going to do is I am going to put my parenthesis. I'm going to put 3.8 times 10, a to the b, and I'm going to the 8th. I hit the forward arrow and then close my parentheses. We're not done yet. Remember, you have to square this. So then you hit a squared. And that gives us our answer, which is 2.5 times 10 to the 20th newtons. Okay? Again, it's a lot of typing, but it's not that hard. It's the same thing. As long as you got your numbers right, you just got to know how to put it in the calculator. Okay? Let's do another one. Okay? So again, the answer here was 2.05 times 10 to the 20th newtons. Boom! That's how much force there is between us and the moon. That's a lot. All right, next question. How much force is there between two objects? One object is 6.2 kilograms. The other object is 58 kilograms. Okay? 62 and 58 kilograms. Hey, thanks. Okay? If they're 2 meters apart. All right, so we have the same equations, okay? Again, we have our mass number 1 is equal to 62 kilograms. Our mass number 2 is equal to 58 kilograms. And big G is always 6.67 times 10 to the negative 11th. And our distance here is only 2 meters. So really what this is this is two human beings standing about 6 feet away from each other, socially distanced. How much gravity do two human beings that are socially distanced have on one another? Well, we're going to use the same equation. Big G times m1 times n2 divided by they call this the radius. It's the distance squared. Okay? So watch this. All right. We go, so the force is going to be equal to, let me see if I can get it away from that corner. So force is going to be 6.67 times 10 to the negative 11th times 62 times 58 divided by 2 squared. This one's a little easier to type in, so it should be a little easier. Again, calculator, clear everything, okay? Parentheses, 7 times 10, a to the b, negative 11, because it's a very small number, forward arrow to move it down. If you don't do the forward arrow, here's what happens. Oof, oof, we don't want that. That's very bad. Okay, forward arrow, close parentheses. You can also just use the keyboard to close the parentheses, which is nice. Oh, I hate it when this happens. Where is... There we go. Okay, times 62 times 58. Notice I don't have to put 58 or 62 in parentheses because they're just numbers. Again, I hit enter, and then I hit answer, which is that answer that I just got. You can see it right here. Oh, okay. And then we're going to divide that by 2 squared. Divided by 2 squared, because it's the distance squared. Enter, and you get 6 times 10 to the negative 8th newtons, which is pretty much nothing. That is an undetectable amount of force. But there is something. Remember, we did say that there is some amount of force between every object in the universe. So if you're standing socially distanced from somebody, there's some gravity there. All right, one more. Let's do one more, because this last one kind of shows up as a trick problem, and I'd like you guys to see it. All right. What is the force of gravity between a 65 kilogram person and the Earth? Now, you got to think here, and I should have put this in here. What if I put, what is the force of gravity between a 65 person standing on the Earth? Okay? Meaning, instead of there being a distance between the two of you, it's more like this. Here's the Earth, here's you. Okay? Well, there's no distance between the two of you. Yes, but there is distance between you and the center of the Earth. Okay? So this right here is our radius, or our distance, right? Radius just means the distance to the center of something. So that's why we put r here, because we measure it from the middle of this object to the middle of this object. All right, well, we know the mass of the Earth, boom. We know the mass of this person, boom. And we know the radius of the Earth, meaning the distance from us to the center of the Earth is 6.37 times 10 to the 6 meters. It's a lot of meters. It's like 6 million meters. We also know big G. Now, do we care about how tall we are? No, because this is like 6 million meters, and you are less than 2 meters tall. So you are negligible in this thing right here, all right? Okay, so same equation. Force of gravity equals big G, 6.67 times 10 to the negative 11th, times the mass of the Earth, which is 6 times 10 to the 24th. This 0.0, right, doesn't mean anything. You can put it there if it makes you feel better. Times our mass, which is 65, divided by the radius of the Earth, 6.37 times 10 to the 6th. And remember, you always have to square the distance. Very, very important. You got to square the distance. Go to our calculator. All right, okay, you can almost see it. See that parenthesis? All right, let's do it. Parenthesis. Boom. Ooh. Excuse me, clear. Parenthesis. 6.67 times 10 to the negative 11th, forward arrow, close parenthesis, times, oh, I guess you could just use that button right there. Close open parentheses, 6 times 10, a to the b, 24, and I guess you could just hit this button. Yep, that works too. Close parentheses, times 65. There's your masses and your big G. Enter. Answer, 2.6 times 10 to the 16th. And we're going to divide that by the radius, which is, close parentheses, 6.37 times 10 a to the b, 6. Whoa, look what I did. See what I did there? Don't want to do that. Forward arrow, close parentheses. And then we're going to square all of that. And look at this. That total force is 641 newtons. Now, for all you big nerds out there, I'm going to show you something. This answer here, right, is 641 newtons. This is our force of gravity between somebody that weighs 65 kilograms, right? That's what we just calculated. Now watch this. You may be thinking, wait, I remember calculating the force of gravity before. Isn't the force of gravity between a person and the Earth just equal to their mass times the acceleration due to gravity? Which would be their mass is 65 and the acceleration due to gravity is 9.8? Really? Isn't that, Mr. Norris, didn't you tell us that? Isn't that right? I did. And watch this. See how this is 641? 65 kilograms times 9.8 meters per second. Ah, did you see that? Is 637 newtons, which, all things being considered, is pretty much the exact same answer, right? There's some decimals missing off of these numbers. We rounded them, but look, we get the same answer. Isn't that cool? Science is cool. All right, guys, so remember, write down the equation. Know how to find what happens when you double the mass or when you double the distance, okay? And understand how to put the numbers into the calculator here. That's the most important thing. Just take your time, make sure you put the numbers in correctly, and you'll do great. All right, guys, be good. Email me if you got any questions.